Hello and welcome to Thursday's edition of Cracking the Cryptic and a puzzle from the maths professor Dorlir called Threads of Silence. And we are told this is one of Dorlir's he is most proud of this puzzle, so it must be incredibly good. It's very pretty, I will say that. And it's got 4 stars out of 5 for difficulty on Logic Masters. And I will tell you that overnight we received an email from none other than Marty Sears saying that this is just so spectacularly brilliant. So I've bumped it up in our queue. I'm going to have a go at it today, and we'll see how I get on. Well, hopefully I will be able to solve it, and this will become a video. But we'll have to see. In due course. I'll read you the rules. I think, well, the rules are pretty standard. This line is not a very standard line. This has some sort of mod 5 property, which I haven't seen before. But we'll talk about it more in a moment or two's time. Now, what can I tell you about before we kick off today? A few things. We're streaming again next Monday. We're going back to the Blueprints Mansion, so we'd love to have your company if you're free for that. I'll try and remember to put a link on the screen. Over on Patreon yesterday, and by the time this video goes live, if indeed it becomes a video, there'll be even more videos in my series of attempts at a puzzle called Spyder by Sabre. Let me just show you this. So this is the crossword, and yeah, it's a fascinating puzzle, and it's also quite hard, and therefore I've recorded a whole series of videos of my attempts. We released 2 yesterday, and there have been some lovely comments actually so far, so thank you very much if you did watch it and you have enjoyed it. I do enjoy reading the comments on these, and then there'll be 2 more that should be live by the time this video goes out, and then there'll be well, I won't tell you how many, but there'll be more tomorrow as well. So it's a whole series of me trying to crack this. Now, the other thing is we're closing in. We are getting towards the 1st of October. And I just wanted to, I don't know if you'll be able to see this properly, but this is what we've got coming up for you on the 1st of October. This is a pack of puzzles by the Skunkworks. All of these puzzles are sort of 6x6 puzzles, snacky puzzles. And just look at some of the names here. There are 68 puzzles, and if you've got good eyesight, you'll be able to see some of the names. And there are lots of names on the setters list here that you'll be familiar with if you've been watching the channel for any amount of time. It is an absolute tour de force, and yeah, I think something everybody must be looking forward to. You can see occasionally the puzzles have 1 solve, apart from our puzzle at the end, which has 3 solves because of testing. But anyway, that's going live on the 1st of October over on Patreon, so do check that out. What else can I tell you about? I've got 2 birthdays to do. I'm going to start off by saying a very happy birthday to Albin. Albin, your friend Leon wrote to us and claimed that you were a sort of mega viewer of the channel. I hope that's true. I hope you have a brilliant birthday, Albin, today. I don't know anything more than the fact that you watch. I hope that, of course, there is some chocolate cake in store and it's heavily iced. And somebody who is definitely a mega viewer is Vicky. Vicky's turning the big 4-0 today, and found us actually originally during COVID. I remember this. Dave Gorman, the comedian, wanted to try and get people into cryptic crosswords. So he did a sort of a Zoom, is it a big Zoom call? I don't know what you call them, but like a big Zoom showcasey thing, trying to explain cryptic crosswords. And I was asked to sort of take part in that. And Vicky discovered the channel then, and then claims to have watched every single solve that we've released thereafter. I'm not sure that can be true, but if it is, my goodness, Vicky, thank you so much for spending so much time with us. I enjoyed hearing that you find the community genuinely friendly and encouraging. It is. That's a testament to all you guys watching. It is a remarkable place in the internet nowadays, the Cracking the Cryptic world. Yeah, Vicky, I hope you do get some chocolate cake today. Many happy returns. And I hope, of course, the icing is delicious. That's all the news. Let's have a look at the rules for Threads of Silence by Dorlir. The rules are as follows. We've got normal Sudoku rules apply. So we're going to have to put the digits 1 to 9 once each in every row, every column, and every 3 by 3 box. Now, okay, every run of 5 digits on the yellow line contains a digit from 1 to 6, a digit from... No, not from 1 to 6. It contains a digit that's either 1 or 6, a digit that's either 2 or 7, a digit that's either 3 or 8, and a digit from 4 that's 4 or 9, and the digit 5. So imagine that square was a... Let's make that a 4. What is that saying? Every run of 5 digits. So 1, 2, 3, 4, 5. So that set of digits would have to include, one of those would have to be a 5, one of those would have to be 1 or 6, and I think this one, because in that set of 5 digits you wouldn't have had a 4 or a 9, so maybe that one has to be a 9 in this instance. That is a really weird rule. I don't know, I should understand it better, shouldn't I? But I do vaguely understand it, I'm just not used to it. Okay, what else? We've got other types of lines. I think the other types of lines are more regular. The grey line consists of 1 or more contiguous groups of cells, each of which sums to 10. These groups of cells cannot overlap. So if this was a 2, that could be an 8. And then you could go 4, 6, 5, 1, 4, 3, 7, perhaps. Forgive me if I've made a Sudoku mistake, but the idea there would be those would all be each of these segments contains digits that sum to 10, and that is how the grey line will work. Now, digits an equal distance from the centre of the purple line. That is a genuine purple as well. It's not like my attempt at purple. This is my attempt at purple with the shading. That is actually maybe I should change my, because that is really purple and that is more clearly pink, isn't it? Goodness, that's food for thought. Anyway, what does it say? It says digits an equal distance from the centre of the purple line must sum to the digit in the centre of that purple line. So if that's a 9, these two squares could be 1 and 8, and then these two could be 4 and 5, for example. Oh, not 4 and 4, because 4 and 4 only add up to 8. So 4 and 5 would work. They add up to 9. That's all the rules for the purple line. Adjacent digits along the green line must differ by at least 5. So if that's a 1, this square has to be 6, 7, 8, or 9 in order to be sufficiently different from 1. And only one more rule. Digits on the pink line, genuinely pink line, form a set of consecutive integers in some order. Form a set of, yeah, that's normal. So if this was a 1, 1, 2, 3, 4, yeah. So this is a length 7 line. So this would have to contain the digits 1 to 7 now, and they can be in any order. So you don't have to. It's not like a thermometer. We can put them. That would be a totally legitimate way, I think, of filling that line. And they are all the rules. Do have a go. The way to play is to click the link under the video as usual. But now I get to play. Let's get cracking. And I'm not going to do what I did yesterday. Yesterday I did this puzzle. It was absolutely phenomenal. It's such a beautiful puzzle by mathguy_12. And I overlooked an obvious opportunity to use set early in that video. I'm not sure how much it cost me, but today this is screaming Ard's set at me, Ard van der Wetering set, which I can never quite remember, but I know how to prove. And what am I gibbering on about, you might wonder? Well, let me explain. There is a principle. Let me just do some colouring quickly. Oh, that's a horrible choice of colour. Blue? Yeah, that's better. So Okay, so let's prove this together, and then we'll work out what the sets are. So I've just highlighted some blue cells in the grid. Now those blue cells, I've got no idea how the digits are disposed within the blue cells. I don't know if this digit's a 1, it could be anything, I don't know. But I do know, as a collection, exactly what the blue cells contain. Because of course I've just highlighted 5 complete rows of the puzzle. And each row, because of the rules of Sudoku, contains the digits 1 to 9 once each. So the blue digits are definitely 5 sets of the digits 1 to 9, aren't they? Now, if I was to highlight in a different colour, is that clear? I think that's pretty clear, isn't it? Or maybe I should use orange, because I think orange and blue are meant to be. No, I can't really see that against the... Or maybe I use black. No. Sorry, I'm just trying to do it in the most distinct colours I can. Right, so I've highlighted some different cells, or a slightly different set of digits, in green. And you can see that I've highlighted the final 4 columns entirely in green. Now, therefore, the green cells comprise 4 sets of the digits 1 to 9. So the blues are 5 sets of the digits 1 to 9. The greens are 4 sets of the digits 1 to 9. Now, actually, might as well remove that. If I remove that from the blue set, I've just removed 1 set of the digits 1 to 9 from blue, haven't I? Because that's a complete box of the Sudoku. So now what remains in blue is 4 sets of the digits 1 to 9. What's in green is 4 sets of the digits 1 to 9. So these are equal sets. These are the digits in blue are exactly the same as the digits in green. Now what would happen if I remove this cell from blue and from green? So let's imagine I do that. What can we say about what remains in blue and what remains in green? And the crucial thing to get your head around is, well, the blue cells and the green cells contained exactly the same thing, and then I took the same thing out of both. So what remains in blue and what remains in green must be the same. These digits, or the contents of these cells must still be the same. We now can't say it's sort of 4 sets of the digits 1 to 9 because we don't know what this cell contains. But we do know that what remains in blue must still be the same as what remains in green. And of course we can do that for all the cells that are sort of bichromatic. And this is Aard's trick. So Aard van der Wetering, the great Dutch constructor, noticed that in any Sudoku, the cells that are in blue are going to be the same as the cells that are in green. Now it's all very well noticing that these lines seem to be implying this, but what I don't know is what it means. Hang on, now I need to go back to the rules. Sorry, what are the rules? Oh, this one, okay, that one is a multiple of 10. And this is a zipper. Let me just mull this. Sorry, I need to think about this. There must be a mathematical relationship, mustn't there, between... So this is a Renban. That is a 7-cell Renban, so it sums up... Well, it depends on its contents. It's either got 1 to 7 on it, which sum to 28, or it's got 2 to 8 on it, which sum to 35, or it's got 3 to 9 on it, which sum to 42, I think. So, what, if anything, does that mean? So this is going to be a multiple of 7. This is going to be a multiple of 10. And the zipper, well, the zipper, if we make that, imagine that digit's x. Those two sum to x, those two sum to x, and those two sum to x. So that part of the zipper is a multiple of 4. And by the secret, that box The secret. Well, that box sums to 45, which is a multiple of 5. So there's some sort of multiplication point that we're going to have to figure out, I think. But the secret, I sort of elided over it slightly. What is the Sudoku secret? How did I know that these cells sum to 45? Well, the secret is something I share with only my very favourite people. But if you're watching this video, of course you're one of my favourite people. I know that this box adds to 45 because of the rules of Sudoku. I know the digits in this box are the digits 1 to 9 once each, and the triangular number for 9, i.e. the sum of the digits 1 to 9, is 45. So I do know that the sum are... So yes, okay. Yeah, that's lovely, actually. So I do know that the sum of green is odd, because I'm adding an odd number, the number 45, to something that is a multiple of 4. And now a multiple of 4 is definitely even, so I'm adding an odd number, 45, to an even number, and I must therefore get an odd number. Now, I know that any multiple of 10 is even, so the sum of the digits on that pink line must be odd. And that means they're 35, because that was the only odd number we got. I worked out these were multiples of 7. It's either 1 to 7, 2 to 8, or 3 to 9. And the only one of those that's odd is 2 to 8. So this is the numbers 2 to 8. And that means... Well, that means that this line has got 1 and 9 on it. It is so weird. It's like we're passing the digits backwards and forwards. So sorry. Let me just. I mean, this is an absolute nonsense pencil mark, but I just want to do it just for a second to explain something. So the only way of making that pink line have an odd total was to make it the digits 2 to 8. And you may say, well, how did I know that 2 to 8 added to 35? I didn't add them all the numbers. I just knew that the numbers 1 and 9 were missing. And because of the secret, which I know the sum of the digits 1 through 9 is 45. If I miss out 1 and 9, it's not too difficult to get the 35 for the remainder. Now, if this adds up to 35, well, no, the point is that that box there contains the digits 1, 2, 3, 4, 5, 6, 7, 8, and 9. And this line contains the digits 2, 3, 4, 5, 6, 7, 8. So the difference between this box and this line is just the digits 1 to 9. But because we know the sets are equivalent, that means that this has to have 1 and 9 on it. And in fact, they're going to be a pair, aren't they? Because once 9 is on this line, it must be collectible with other digits that make a sum to 10. And the only thing we can add to a 9 to make 10, we can't add half to it or something. That doesn't exist. So so the 9 and the 1 are effectively a pair on this line somewhere. And then the other digits on the line are going to... Yeah, so so now the other digits on the line are still going to be a multiple of 10, because 1 and 9 add to 10. And then, so imagine this was the 1 and the 9. Then we've got an equivalence between those cells and this part of green, which means the zipper would have to contain exactly the same digits as this part of the line. And we know this is a multiple of 4, and we know that what remains on that line would be a multiple of 10. So how does that work? So that means... Okay, so if that digit is X, let's just put X in there. Sorry, I just want to think about this. So what I'm saying is those 7 cells sum to 4 lots of x. X plus another x plus another x plus another x. So this is 4x. And then these cells, well, not only would they sum to 4x, but they would be 10 times y, where y is the number of 10 segments in this section. So 4x equals 10y, which means that x itself is 5 times, yeah, so x itself is, yes, sorry, right, I'm getting there now. This is beautiful. This is x is 5. Right. So what we've got is an equation. We've got an equation. So hang on, I've got to sort of explain this. So this is 1, 9. It might well not be, but I know 1, 9 exists as a pair somewhere on this line. So let's just imagine it's there. So this part of blue is the exact equivalent to that part of green. So this is the exact now equivalent of this. But because this is a 10 line, this is going to be some number of consecutive segments, each of which sums to 10. So I'm expressing it as 10 times y. So I've now got 4x on that part of this line equals 10y, which means that because if we can take the common factor out effectively, which is 2. This is right, isn't it? Then I've got 5 over 2. So I've got x equals 5 over 2y, where y is the number of segments on here that sum to 10 that aren't this segment. And therefore, what can this digit be? It's 5 over 2 times an integer. Well, if I make that integer 2, then x can be 5. But the only other way of making this an integer would be to make y 4, for example. But if I do that, this becomes 10. So this is a multiple of 5. And if it's a multiple of 5, the only Sudoku digit it can be is 5, which is actually a really weird result for many reasons. The reason it's weird is that means these digits, well, in fact, all of those digits are really tiny because they've all got to sum to 5, so they can't even be as high as 5. So we've got to get rid of this. This is really, really interesting and quite weird. 5. Do we have to do 5 in this box now? Because I haven't talked about the whispers principles at all, but there are some. So the green line, adjacent digits on this green line, have to differ from the next digits by 5. Well, imagine this was a 5. What would this digit be now? It would either be 5 less than 5 or more, 6 less than 5, 7 less than 5. Well, that's negative numbers or 0. That doesn't work. And if we increase 5 by 5, we get 10 or higher. That also doesn't work. So there are no 5s on this green line. So 5 is in one of those two positions. Actually doesn't interfere with this 5, does it? I also know that this line is split into exactly 3 segments, don't I? Because there's the 1 and the 9 was one of the segments, and then the y, which was my total number of other segments that summed to 10, in order to make this 5, that was 2. So there are only 3 segments on this line. But we could repeat digits on it, I think. You know, if you went round the corner there, those 2 digits could be the same. Yeah, actually that's quite an... Yeah, that is interesting. Hang on. Y was 2. So this entire line sums to 30. Because there are only 3 segments on it that sum to 10. Now, one of the segments is 1, 9. So the other digits are going to have to add to 20. And that feels quite difficult all of a sudden, doesn't it? Because, well, imagine that's 1, 9. I mean, the minimum they could be would be 1, 2, 3, 4, 5, adding to 15. So the maximum they could be would be adding up to 5. How do we know exactly what the composition of this line is? I think we might be able to work it out. Does that have to be 9? If that's 9, no, that doesn't quite work, does it? If that's 9, that could be 1, 2, 3, 4, that could be 1, 2, 3, 4, and that would be 20. Now, see, that's really close to a minimum, actually. That's really close, because I know the line overall adds up to 30. And if this is a 9, and that's 1, 2, 3, 4, and that's 1, 2, 3, 4, that's 29. So if that was 9, we would know how the line was made up. This would be 9. One of these would be 1, 2, 3, 4, and the other would have to be 1, 2, 3, 5. That's the only way of splitting the 21 we would need into valid segments. But I'm not sure that that's actually... I'm not sure I can therefore just allege that this line is 9, 1, 2, 3, 4, and separately 1, 2, 3, 5. It might be. But if the 9 wasn't here... So say this was 1, 9. I mean, I can only put 2 1s on the line, can't I? Because I can't have more. I can't have 3 1s on that line because there's only 2 Sudoku units. There's row 5 and column 5. So so the best I can do, let's actually do it that way. The best I can do would be to have 2 1s, 2 2s, 2 3s. No. Okay, I could do the 3 there. That will allow me to have 2 4s. If I didn't do that, I couldn't have had a 3rd repeated digit. Or a 4th repeated digit, sorry, because if I'd gone 3 3, then the minimum these could have been would be 4 5 and 9. Whereas if I go double 3, if I put this 3 here, I can then go 4 4. And I haven't clashed anything, and that would be 9. So actually, no, I'm now coming to the view that I think I do know the contents of this. Because that is clearly the absolute minimum. Given I know it's got 9 on it, the absolute lowest I could go would be 2 strings of digits that each add to 10 around the side, which wouldn't get me high enough, but I've only got 1 degree of freedom. So I've got to have... I think I've got to have a repeated 1, a repeated 2, a repeated 3. If I don't have repeated 3, and instead have repeated 4, for example. I think I'm just going to blow the total. Let's put the 4 there. Have a 3. Have a 5. Have a 9. How high is that? 12, 10. It's too big. It's 31. So there is definitely repeated 1, repeated 2, repeated 3. There is a 9, and the only other digits that we can include, we can't repeat any digit more than once, so there's going to be 2 maximum of any digit on the line. So this line is 1, 2, 3, 1, 2, 3, 4, 5, 9. And this, okay, this is going to be good, isn't it? Because I have to repeat 1, 2, and 3 on the line. Oh, does this not do anything? This must do something. Oh, well, here's a different point. Because I have to repeat 1, 2, and 3 on the line, obviously this junction of the line can't be 1, 2, or 3. That's going to prevent me repeating those digits. Now, that means this digit is 4, 5, or 9, which are the other digits that I have at my disposal. It's not 5. So that middle digit is 4 or 9. Now, if it's 9, it has to have a 1 on one side of it. If it's 4, I'm less sure. I'm less sure what. I sort of feel that the line must be. It feels like the 2 10 segments I've got that are not 1 9 are going to have to be. So I've got 1 and 9. Oh yeah, I know what it's going to be. It's going to be a 2 3 5 segment, isn't it? That's what it's going to be. And then a 1 2 3 4 segment. I'm just pausing. I'm wondering whether I could have 5 2 2 1 or something. I don't think that will work though. I think I'll then won't be able to repeat the digits in the correct positions. I'm not sure. I might be missing the point actually. There might be something easier. This line does not feel very easy to figure out. Those are not 8s. Actually, I should probably take this out. It's such a ludicrous pen. It's a ludicrous pen. No, I don't know whether to take it out or not. I won't remember, will I? It's 2 to 8 if I take it out. What's going on the Whisper? I mean, we talked a bit about the Whisper earlier. This is... It can't have 5 on it. And what that means is that every digit on the Whisper either has the property of being below 5 or above 5. And the crucial thing to realise is that let's imagine this digit was below 5. This digit can't also now be a below 5 because it wouldn't be 5 apart. So this digit would have to be the other side of 5. And now this can't also be higher than 5 because these can't be 5 apart. So this would be lower than 5 again. So what's going to happen on this line is oscillation. Those digits are going to be of... Actually, let's pick a different colour. Red, maybe. And the other digits are going to be... the other digits are going to be the alternative colour. So we've actually got 4 of red in box 3, which means that red is either 1 2 3 4 or 6 7 8 9. Right. I don't know what the answer to that is, but I do now know that these are from 4, 5 and 6. And that's because 4 and 6, 5 is impossible to put on a green line, but 4 and 6 are jolly difficult. So let's think about what 4 could partner up with. We need a digit that's at least 5 different from 4. The only Sudoku digit is 9. So, and imagine 6 was on the line. What would that be next to? Well, it would only partner up with 1. So look at these 3 blue cells. and ask if they could be 4 or 6. And the answer is no. If this was 4, it would have double 9 around it. If this was 4, it would have double 9 around it. If this was 4, it would have double 9. So none of these can be 4, 5, or 6. So 4, 5, and 6 are in these cells. And one of these two digits is going to be 4 or 6. So one of these two digits is going to be 1 or 9. Now, what does that mean? Oh, no. Right, let's change tack a bit. Actually, I've seen something different. Okay, right, look at that domino. I know that might not be the world's most obvious domino to look at, but obviously you've got one higher than 5 digit here and one lower than 5 digit here. Well, the lower than 5 digit here will be a 1, 2, 3 or a 4, and it will partner up with these, won't it? And that's going to make a quadruple in the box. So these digits are all great big digits. Oh, forgive me, I am just going to notate that for a moment. Just to see if I can understand what that means. I mean, the same is true in column 6, you know. One of these digits is a low digit. So in this column, we're left with 6, 7s, 8s and 9s into those cells. That might actually almost be more useful. It looks like there's some... Oh, see, if that was a 9, these digits would be 5, 6, 7, 8. These would be 1, 2, 3, 4. That would work beautifully, because that would be a 10 segment. This would be a 1 to make a 10 segment there, and then that would be 2, 3, 5. Now, if that's 4... No, I'm not sure. I think that could work. I mean, if that was 2, 3, 5, 2, 3, 5, and that was 1, 1, 4, 2, 3, 1, 9. I'm not sure if I repeated a 1 then. I got... Oh dear, I don't know what to do. I'm sorry. I don't think it's this line. What was I can't even remember the rules for this line. This line, this is the mod 5 line. Yes, oh, okay, so there is a 5 in one of the... Yes, sorry, I hadn't thought about this line, but this line, it has the express... Every 5 digits, you have to put a 5 on it. Oh, Simon, sorry, right. Yeah, look, where's 5 on this line? In that 5 cell segment, there has to be a 5. So it's in one of those two. And in this segment, okay. And in this segment here, that's 5 cells of yellowness. So if one of them has to be a 5, well, it can't be those two, because I've got a 5 in one of these. So there's a 5 in one of those. And there's a 5 here. Right, so now there is a 5 up here. So there is not a 5 on that stretch of my pink line. There is not a 5 here either, actually. There's not a 5 here because of this 5. So there is a 5 in one of those two cells. That one of these two cells contains the 5 on the pink line, which means this is not a 5. Now, what does that mean? I've got a horrible feeling I've got to think about the grey line again now. Oh dear, oh dear. Let me just mull this over. Let's think about this. Okay, so if there is a 5 up here, I know, so that I'm just thinking about how we can possibly make the 10 segments, the 3 10 segments that exist on the green line, the grey line, from the digits that we know occupy it. We know there's a 1 and a 9. And we know there's a 5. Now, if the 5 did partner up, not with 2 and 3, but with 1 and 4. So imagine up here it was 5, 1, 4. This would be 9, and that wouldn't be able to be filled. So that's nonsense. So I think this top section has to be 2, 3, 5. We can't put 2, 3, 5 as a segment there because that would have to be an individual 10. Yeah, so this is 2, 3, 5. Just that's the sort of only way it can possibly work. Now there's a break in the 10 line here. That's the world's worst choice of colour to show that. There. Then, okay, so this, well, hang on, we know 1. 1 has to make an appearance here, doesn't it? Because 1 repeats on the line, so that's a 1. Now, so this is not a 1. I feel like this is going to be a 9, but I'm not certain. If that was 4, and this was a 2, 3 pair, and this was 1, 9, is that valid? Thing is, I don't know. It might be. It really might be. I'm so sorry if this is... I've a feeling this is obvious to everybody. That devil on my shoulder is chirping away and telling me I'm being an idiot, but I'm not sure I do know. If I do, I apologise. I'm sorry. I don't know. You guys might know. Right, but that's... okay, so 2 and 3 are not in that one anymore. Ah, no, that doesn't work, actually. What I was about to say is not true. I don't know what to do. Oh dear, sorry. Okay, there is... Okay, I do know exactly what these digits are now, though, don't I? These are 1, 2, 3, 4, 9 in some order. So this is a 1, 2, 3, 4, 9 quintuple. And therefore 9 doesn't live in those cells. Now, what, if anything, does that mean? Oh, I've got it. I've got it. Right, it's not this. That's not the point. It's beautiful. It's beautiful. The point is this. I know that this pink line has these 3 digits on it. Now I haven't got a clue where they go, but I do know they're in those digits now. 2, 3 and 5. And why is that exciting? Well, it's surely exciting for this domino. Because I know either indigo or red is a low digit, a digit lower than 5. And now that cannot be 1 and it cannot be 2 and 3. So it is 4. And 4, we learned up here, is totally monogamous. It only partners up with 9. So whichever one of these is 4, that is a 4-9 pair. And one of those is a 9 as well. Because imagine this was 4. You'd have to put the 2 9s in red. If this is 4, you've got to put the 2 9s in indigo. So now... okay, so now 4 isn't in any of those cells. So 4 is definitely up here. So now the low digit that's in this pair is not 4 or 2 and 3. So it's 1. Which is a much less... oh, well, I was going to say it's much less exciting, but that does mean that this is 2, 3, 4. Actually, look, there's something going on now on this zipper line. Hang on, I think I just removed the wrong thing. I wanted to remove 4 from there, and I managed to remove 1. So, what, if anything, does that mean? 9, hang on, 9 comes out of those cells. And, oh, Bobbins, this is close now to doing something, isn't it? I don't know. It probably is. One of these is a 4, so one of these is a 1. 1 is there. Is that one? Is that one? Yeah, that one is genuine because 1 has to repeat on the grey line. Gosh. So this isn't a 1. So one of these is definitely a 1. I want to know this digit. I really do. I feel like I should know it. And I'm being a bit too dumb to work it out. It's really strange because I keep thinking, oh, I must understand it now, and I'm not sure I do. What about? I just don't know. Sorry, I don't know where to look. It can't be this line, can it? I mean, oh, hang on. Okay, no, it might be this line actually. Every 5 digit. See, what I haven't done is I haven't shaded this line. And I was just looking at that cell and I was thinking about its modularity. So whatever it is, so it could be a 1 or a 6 modularity or whatever, that then has to, there's going to be 5 cells in which this modularity can't repeat. And then that cell is going to have to be the same modularity as that one. And that one. So these 3 are actually all the same modularity. So I don't think this can be 5. Because that should be a 5 then, and this should be a 5, which definitely clashes. So this one is the same modularity as that one. That is interesting actually. So this one is the same modularity as that one. I might get to a point soon where I have to repeat colours, I'm afraid. I don't mean to do it, but so 5s work. Oh, that's huge. Right. 5s, I was about to say 5s work beautifully in these positions, but they definitely don't work perfectly in those positions, do they? If both of these were 5, let's use lime green. Well, point is, if that's a 5, that's also a 5, and that breaks Sudoku. So this has to be from a modular pair, i.e. where there's a choice like 1 and 6, for example. So those are 5. And sorry, I was sure that was going to do something, but apparently... Oh, that's extraordinary. Apparently that does nothing. That's weird then. So which line? Is it this line? Or maybe it's the Renban. So I've got 2, 3, 5 here. So I've got 2, 3, 5 here. I don't think I can do anything with that one. I don't think I can do it. I do know one of those is an... that's not a 9. That's it. The fact that I've got a 9 in one of these means this isn't a 9. Now, I've got a 4 up here, and then 2 of the digits, 6, 7, and 8. So the simple question is, where is 9 in box 2? And it's on the whisper with a 1. So this is a 1. Oh, that's not done anything. This is a 1-9 pair. But that is a 6, 7, 8 triple, which I've already apparently known about. So if that was 9, these would be 6, 7, and 8. And this would have to be 6. And that's... Oh, 9 is in one of those two cells, because 9 needs to find a home in column 7 somewhere. And I think if that's 9, it'll be, then these would be 1, 2, 3, 4, wouldn't they? Oh no, that's not easy. That's not easier actually, because of that given. Yeah, that's so sneaky. That's so sneaky. Right, that's it. If this is 9, there's a problem in this box with the whisperage, because if that is a high digit, these two have to be high, and one of them is going to have to be a 6, and neither of them can be, because neither of them is allowed to be 8 by Sudoku with the given. So the only high digits available are 6 and 7, and whichever one of these is 6, it will be surrounded by double 1, and Sudoku will break. So there you go. That's probably been available for ages. So these are both 9. Therefore, this is 4. Now that means I can see what that's going to mean. So now these have to be 6, 7, and 8. This definitely isn't 8 or 6. That can't be 6. So this is 6, this is 7, this is 8. 7 must be surrounded by 1 and 2 on a whisper. That's the only legitimate digits. You can see that this is just unwinding. It's just beautiful. This digit here is going to have to be a 3. 4 would be too close to 8. And these two right, so this digit is a 5 now. This digit is a 4. So Sudoku is almost coming into... Sudoku is almost being kind to us, isn't it? So this digit is not a 4. So this digit is not a 1. This digit is not a 3 either because of this. So this digit is not a 2, I'm going to claim. That digit's not a 3. So that digit's not a 2. I've got, oh I see, there's a 1-2 pair here. Is that really true? Oh, that's huge. Yeah, look at column 9, there's a 1-2 pair. So that digit's a 4, which makes this digit a 1 by Sudoku. It might not do anything, but oh no, that's beautiful. That does do things. That does do things, because now look, that's a 1, that's a 2. Now this has to be 3. Now we know these two add up to 5 again. This is a 2. That's a 1. So we actually this whole zipper has now, it's been unwound by the whisper working. Yeah, that's beautiful. That is beautiful. Now, I was going to say, I'm almost tempted to get rid of all my colours, but do you think we should? What purpose is... I don't think green is serving any purpose. I don't think blue is serving any purpose. I don't think this is serving any purpose anymore. This might still serve purpose. But look, we can do a little bit of tidying up at least along here. 5, 3, and we're going to be chocolate teapotted, are we? I must be able... Right, that's not 5. That's not 8. 6 comes out of both of those squares. That's not 7. That's not 8 or 6. This is not 4. And something's got to unwind somewhere. What do we do now? Column 9 needs 5, 6, and 7 into it. That corner isn't 5. Sorry, I know I've stopped talking. I don't know what to do. Yeah, these two digits, which are from 6, 7 and 8, do have to appear on this pink line. So they are going to be up there. So those two digits are up there, along with the 4. How can I not know this digit now? That's so distressing. Or is it? Okay, I see. Right, where do we put 2 and 3 in box 5? They are there. That's Sudoku. Now, I say that like it should do something. I think it probably does something. I just don't know what. No, come on. Come on, that's got to do something. Does it affect? No, it doesn't. It doesn't affect this. I still don't know whether this is a 4-cell segment like that with a 1-9 pair here, or this is a straightforward 1-9 segment and that's a 1, 2, 3, 4 there. So I think I've missed some sort of clever trick that I could spot there. I don't know how to do that. Actually, I'm not going to say anything. I was going, oh, there has to be a 4 in one of those. And 4 presumably goes with 9, does it, on this line? So if that was a 4, that would be 4 or 9. If that was a 4, that would have to be 9. And if that was a 4, these squares would be 4 or 9. Which... the black digit is not 3 or 8, which is a pair somewhere on the line. So how does that work? I don't know. None, actually none. Right, there has to be an 8. Oh, that's it. That is it. Right. Right. So what we actually have to do is look at that segment of this line. Okay, what I noticed about that segment is firstly it's got 5 cells on it. So it has to include one of each modularity. Now, there is a 3 here. So we can't put 3 in any of those cells, which means there's definitely an 8 in one of those cells. Now, the 8 cannot go here. Because if that's an 8, this cell's got a problem. It's meant to be from 3-8 modularity and it sees both. Now, what about... oh, actually, am I wrong here? Hang on, I might be wrong about this. No, I'm not. I was nearly wrong. In my brain, I'd concluded the wrong thing. I do think it is about 3 and 8. Well, it's about 3 not being able to be on this. So we know one of these is 8. We've just shown this cannot be 8 because that one can't be filled. If this was 8, how would that work? Well, that would make this square have to be a 3. And that actually works, which I thought it didn't, but it actually does work. Now, what about if that was 8? Well, then this would have to be 3 or 8, and we already looked at that. That doesn't work. And if, on the other hand, this is 8, then that has to be 3 or 8, but it sees 8 here and it sees 3 here, so it doesn't work. So that is actually the 8, which is not what I thought, but it is true. So now that's 4, 6, 7, which we're going to use over there in a moment. This has to be 3 now by Sudoku, which makes that 3 by Sudoku. We can't, okay, and we can't repeat 8 now, ever on this line, because it's had its 3, it's had all its 3s and 8s. So there's an 8 in one of these, and that cell's an 8 by Sudoku. And this is not 8, but this is 4, 6, 7. So we can certainly take 6 and 7 out of that, 6 and 7 out of that, 6 and 7 out of that. So this becomes 2, 3, 5, 8, which takes 8 out of both of those and makes this 7. And that's 6. And that's 6. Here we go. That 5, that 8. Beautiful. Absolutely beautiful. Now, this can't be 5, so that's a 6, 7 pair. 5, 9 has to appear in this column somewhere. So that's 5, that's 9. That should be a 2. Okay, okay. Calm, calm. This is going better now. So now we can put a 2 into one of those. This digit's a 7 by Sudoku. Therefore, that's an 8 by Sudoku. This column has a lot of things in it, but it doesn't have a 1 in it yet. And the 1 can't go there. So this is 1, and this is 9. And that means this is 4. Which is actually not what I was expecting at all. Now we now know that this segment must be a 1, 2, 3, 4 segment. So that's 2 or 3. This is the 1, 9 segment here. Now, that digit seems to have to be 8, which is perfect. That's fine, isn't it? That's not hurting us. These squares are 4, 6, 7. So let's write that in, and we can... Oh, yeah, well, 1 is the pink modularity, so that's got to be 6. Which means this is 1 or 6 in the corner. It's not 1, so that's a 6. I've written 2 and 4 in here. That's legitimate? That is legitimate. That is a genuine pair. And yeah, so how can if 4 is orange, what are we putting in there? We've got to pick a digit from 4 or 9. Well, it would have to be another 4, so that doesn't work. So that's got to be 2, that's got to be 7, that's got to be 4, and that's got to be 4. That's fine. You can repeat digits providing they don't break Sudoku rules. 6 here means this is 6, this is 7. That digit is available to us. That's got to be 9. We've not put 6 and 7 into the box, so we should do that, shouldn't we? This becomes a 7, 8 pair, which we can write in. This becomes a 1, 9 pair, which I can't write in apparently. Now, okay, this has become a 2, using the power of the 3 there. So that becomes 3, that becomes 2, that becomes 3. We can take 2 and 3 out of these squares, and they become 5 and 8, which we can do the order of using that fair-weathered friend Sudoku to help us. I don't know, but I'm going to look at this column because I've got a 1, 9 pair in it. So I need 3, 4, and 6. So that's a naked single, 6. And that's apparently a 3, 4 pair. So this is a 7 now. That's going to unchocolate teapot this. Oopsie. No, well, it would help if I wrote the right digit in. 7, 4, 6. 7 is here by Sudoku. This column needs a 1. Well, that's a naked single. It can't be 9. So 1, 9, 1, 9. 9 here by Sudoku. This row should be done. 4, 3, 2, 5, 3, something. Being 5, actually, I think. And if I haven't made a Horlicks of this, that's a 2. That is a spectacularly clever puzzle, Dorlir. Again, every one of your puzzles is... I love the way you set puzzles. But that was very special. I can see why you like it. Let's see if it's correct. Yes, it is correct. It is rather wonderful. It's taken me just over an hour. I'm not that unhappy with that. I found it quite difficult to grow. Well, I understood where I was meant to look at the start. But it was very beautiful to prove that was a 5, wasn't it? And there were some lovely ideas in this. I didn't appreciate the power of this line at all at the point at which I was meant to. I'm still slightly worried. I didn't that I should have been able to deduce this precise segment ordering along this line more quickly than I did. I mean, to be honest, I thought this was going to be a 9, so I was quite surprised when the 9, or the 1/9 bit of it went over that side. So my instinct was definitely wrong there, which maybe meant that line was quite more complicated than I felt it should be. And I really like this line as well, and the fact that that could sort of, the fact that we got the 4 up here, that was crucial. That's beautiful. It's just a beautiful puzzle. Let me know in the comments how you got on with it. I enjoy the comments, especially when they're kind. And we'll be back later with another edition of Cracking the Cryptic.